Hello, and welcome to A Gross of Physics. Today is day 64, where we're going to look at a mathematical approach to conservation of momentum. As we stated yesterday, conservation of momentum deals with the fact that in a closed system, the total momentum of the system is constant. In an introductory physics course, we typically stick with two objects involved. So what that means is the sum of the momenta of the two objects before they collide has to equal the sum of the momenta after they collide. If the total is 10 before, the total is going to be 10 after. And the distribution of that 10 is what will change during the collision. Now, we need an equation to govern this, but really the equation is just a matter of calculating the momentum of each object before they hit, and then setting it equal to the momentum of each object after they hit. So what it ends up being is the equation is simply momentum before equals momentum after. So P subscript before equals P subscript after. Now that being said, what we can do is determine the momentum of each separately. So we break each of the terms into as many objects as we have. For our purposes, it will be two objects on each side. The momentum of object 1 plus the momentum of object 2 before they collide is going to equal the momentum of object 1 plus the momentum of object 2 after they collide. Now there's a number of ways that we can denote the different objects. I like to use subscripts 1 and 2 for the two objects. So P1 plus P2 equals P1 plus P2. But then we also need to denote what's before and what's after. And the way I do that is I use a factorial or a superscript above the terms for final. So I'll just do P1 prime plus P2 prime to represent the final velocities. Before, I won't have any prime. So it'll be P1 plus P2 equals P1 prime plus P2 prime. That's our simplified equation for conservation of momentum. Now, some textbooks or some instructors will use I and F to denote the difference between before and after they collide, so initial and final. That would look like P1 sub I plus P2 sub I equals P1 sub F plus P2 sub F. Now, we have four terms, and each of the P terms is broken down farther into MV. So you have M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. So the simple equation of P before equals P after looks a little more complex when we write it out fully. Now remember, the reason there's no prime with the M's is because they stay the same. The mass of the object before and after the collision needs to stay the same. Now, this problems that deal with conservation of momentum will often simplify some of the terms. So maybe one of the objects is stationary to start with. Well, the momentum of a stationary object is 0. The other thing that you have to watch out for is dealing with negative values. Objects to the right, we're going to call positive. Objects moving to the left, we're going to call negative. So you need to denote the sign representing the direction of the objects. If you're going vertically, up or down, up would be positive and down would be negative. But typically the problems that we deal with will be left and right. Now, if we had a problem where an object was hitting another object at an angle, well, the total momentum in a system is constant, but what we'd have to worry about are x and y directions. So you can actually have a little more complexity in your problems and have two-directional motion dealing with conservation of momentum. In that case, the sum of the momenta in the x direction has to equal the initial and final, and then the sum of the momenta in the y direction has to be the same in the initial and final conditions. You can end up with a lot more terms if we have to deal with two dimensions. Now, in our introductory physics course, we're going to deal with a single dimension, but it's just another layer of difficulty if you want to add a second dimension. Remember, though, if we have anything in angles, you're going to have to resolve the vectors into components first. And the reason we can do this is because perpendicular vectors are independent. So the x and the y directions for the momenta are separate from one another. So we'll have two sets of equations. But for our purposes, if we just say P1 plus P2 equals P1 prime plus P2 prime, we're going to be in good shape. Now, different collisions can occur between different objects, and we have two different types of collisions that we're going to talk about. Now, when we deal with these two different types of collisions, there are elastic and inelastic collision. Now, an elastic collision occurs when we deal with objects such as billiard balls, things that are perfectly rigid, when things don't stick together. And what will happen is if you have an elastic collision, and this will happen more as we get into the energy section of the course, if there's an elastic collision, not only is momentum conserved, but also the energy. An inelastic collision is typically when objects stick together, or if there's some deformation of the objects as they collide, and that will show that the conservation of momentum is always conserved, but then the energy will be lost during those collisions. So the kinetic energy is not conserved. What you'll be able to do in more complex problems, in an honors or an advanced placement physics problem, is if you have an elastic collision, you'll be able to solve for more variables because you have more equations. In fact, you'll have an equation for momentum, and you'll also have an equation for energy. With an inelastic collision, all you can be certain of is that momentum is conserved. So no matter what, during a collision, conservation of momentum holds. But in certain types of collisions, like inelastic, you can have a situation where the energy is lost. So elastic collisions, momentum and energy are conserved. And in an inelastic collision, momentum is conserved, but the kinetic energy is lost. Now, I think it's important at this point to do some practice problems dealing with the conservation of momentum. So let's take out the whiteboard and let's do some practice problems now. This next problem involves conservation of momentum. And what's important to realize is that the momentum before has to equal the momentum after. So, if we have two figure skaters and they are pushing off one another, well, what's going to happen is before they push, they have no motion at all. So the total momentum before they begin moving is zero. So the conservation of momentum equation can be quite complex. It could be P1 plus P2 equals P1 prime plus P2 prime. Well, and the ones on the left are before. The ones on the right are after. And before and after refers to the collision or the contact between them. Now in this case, because mv1 plus mv2, m1v1, m2v2, the v's are both zero. So the momentum becomes zero. It becomes a much easier problem. Now, after P1 prime plus P2 prime, we'll say the first skater on the left here is the male skater. So the equation goes like this, m1v1 prime plus m2v2 prime. Primes represent after. We have a 65 kilogram mass for the male and a 50 kilogram mass for the female. So the female is on the right and the male skater is on the left. Now, the only piece of information we need to know at this point is how fast one of them is going, and then we'll be able to find the speed of the other. And we want to find the speed of the male skater. So we're going to try to find v1 prime. And in the problem it says, determine the speed of the male skater after they push apart if the female skater is moving at 3 meters per second. So the speed of this person is 3. Now, if it's to the right, it means it's positive. So if we replace 65 v1 prime plus 50 times 3, we're going to be able to find our answer for v1 prime. So v1 prime becomes, I'm going to subtract the 150 over and divide by 65. So 150, turn it on first, 150 divided by 65 means the male skater will have a value of 2.3 meters per second. And since this was a positive and I brought it over to the other side, it becomes a negative value. So the answer is negative 2.3 meters per second. Now keep this in mind. Total momentum before they collided was 0. The total momentum of after they collide has to be 0. So 50 times 3 is 150. 65 times 2.3 is 149.5 because I rounded, of course. But it's a negative 150. The combination of the two should add up to 0. Now, of course, if we go back to check our answers, we're never going to get them to be exactly the same because of rounding. So in my case, I had 149.5, which is within the tolerance of 0 equals 0. Bumper car problems are a staple in physics when dealing with conservation of momentum. Typically, we have a somewhat elastic collision because they bounce apart, they don't stick together. A normal accident with real cars would inevitably cause them to stick together and lose energy. But a bumper car is an example of a collision where we can assume elasticity, plus no one will get injured during these collisions, so it's a safer environment. Although I've been in some bumper car events that have been quite violent on my neck and back. So with that said, bumper cars are still going to become a common question in physics courses. Now in this case, we have a head-on collision. Bumper cars, it's okay to try to hit people with the vehicle. That seems to be the only place where this is acceptable. But car 1 is traveling to the right at 2. Car 2 is traveling to the left at 5. They collide. Car 1 bounces backwards at 4. We want to figure out what happens to car 2. Now, the one thing that's not stated is the mass, but it does say they all have the same mass. And if we look at our equation, m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. This was our before side. This was our after side. If you set up your givens list within a diagram like this, all you have to really do is separate it at the equal sign. And the way I like to do it is I say double line, equal sign. So I'll put a double line between my two diagrams, and that will represent where the equal sign is going to go. Everything on the left stays to the before, everything on the right stays to the after. If you don't want a visual representation, you could even do this in a chart like the regular givens list we've done. But this will combine a diagram and a givens list all in one problem. Now, since mass is the same everywhere, we in reality could replace the subscripts with nothing. And since every term has an m in it, and they're all the same value, they're going to disappear. Now, v1 before, 2 meters per second, plus 5 meters per second. But the 5 is going to the left, so it's a negative 5. Equals, well, now we have a negative 4, because it's going to the left, plus v2 prime. So in order to solve for conservation of momentum problems, you really need to worry about the direction of motion. Now, if we just look at this, negative 5 and 2 is negative 3 equals negative 4 plus v2 prime. Now I'm going to add the 4 to both sides. And not using a calculator at all, in this case, I get 1 meter per second equals v2 prime. So, car v2 is going to travel to the right at 1 meter per second, according to our calculations. All right, let's look at a problem where two objects are going to stick together. This would be an inelastic collision. And what will happen is the kinetic energy will actually be less than the original in that case. Conservation of momentum is still true. So what we can do is still calculate the final velocity of the objects after they stick together. So what we have is a vehicle traveling to the right at 5 meters per second, and it's a 200 kilogram vehicle. It's going to collide with another vehicle that is 100 kilograms, traveling at 2 meters per second. So that's our before. I'm going to put a double line, and then I'm going to put the two objects stuck together, 200, 100. Now, when they're stuck together, they are going to travel at the same speed. So what this is a situation where we have two objects to begin with, P1 plus P2, but then that's going to equal, double line equal sign, one object. So I'm just going to call it P total because it's not 1 or 2, it's the total of the two, and it's still prime because it's its final speed. All right, M, 200 times 5 meters per second plus 100 m times 2 meters per second equals, now what's the mass of the total? Well, we have 200 and 100, so it's a total of 300 kilograms, and we want to find V, I'll call it T prime, T for total. Now I'll write tot since we wrote tot before. All right, with the calculator, we're going to do 200 times 5, which is 1,000. We're going to add that to 100 times 2, which is 200. So it's 1,200 total. And then divide that by 300. So when we do that, we have V total prime equals 4 meters per second. Now, the 4 means it's going to be moving to the right. If it were a negative value, it means it would be going to the left. But it really doesn't make sense that it would move to the left because both objects were going to the right to begin with. But the 1,200 we had here on the left, if we take 300 and multiply it by 4, we get 1,200. So this holds true that the momentum before, which the total was 1,200, is going to equal the momentum after, which is also 1,200. So you can always check your results. If there's a lot of rounding, it won't be exact. But in this case, we didn't have to round at all. Okay, this next problem involves a balsa wood toy airplane. And I'm going to throw it. It's a 50-gram airplane in total. It's going to move at 3 meters per second. Well, unfortunately, during the flight, there is catastrophic failure, which is often the case with the balsa airplanes, and it breaks into 2 pieces. One of the pieces is 20 grams, and we'll just say the nose flies off because it's got the little clip on it with a big chunk of wood, and it flies forward at 5 meters per second. And what we have to do is figure out how fast does the other piece travel. Now, if we look at this, we've already set up our givens list. And if I just do my double line equal sign, then these 2 terms contribute to the total momentum of the system before this failure in the plane and it breaks apart. So the one thing I'm going to need to do is get rid of the grams. So I'm going to make it mv, and I don't have to do 1 or 2 because there's only one object. And then on this side, it's going to be m1 v1 prime plus m2 v2 prime. Changing the 50 grams to kilograms will be 0.05 kilograms times 3 meters per second equals. Now, I know the second one has a 20-gram mass, so that's 0.02 kilograms. And I know it goes 5 meters per second. But I don't know the mass of the first piece. But we do know the total mass. So if the total mass is 50 and 20 grams breaks off, the rest has to be 30 grams. So the mass of the first piece after the failure is 0.03 kilograms times v1 prime. And if we look, we have one unknown, and it's v1 prime. So I'm going to do 0.05 times 3 minus this term. So this term here was 0.15, 0.02 times 5. So when I subtract that over, I get 0.05 equals 0.03 v1 prime. Divide that by 0.05 by 0.03, and I have v1 prime equals 1.67 meters per second. So maybe this was under some pressure. It flung forward rapidly. This piece still moved forward because we have a positive value, but it moved forward at a slower rate than it started. Total momentum of the system would have to add up to this number of the two pieces in this case, would add up to the 0.15. So that's how we do a situation where we have one object to begin with, and then it breaks apart and turns into two.